Everybody, I'm recording this sitting outside my kids' gymnastics lesson in the parking lot, so I apologize for any weird noises in the background. Like I said in my email, I just thought it would be better to have another day where we don't meet in person. It seems like a lot of students are very stressed, which is understandable. A lot of people went home or are traveling, but I will, after convocation, scurry back to my office and fire up Zoom. So if you would like to talk about this material or the material from last time face to face, we can do that. So like last time, it's not particularly exciting to listen to my voice as I hover my mouse over this PDF. So I'm going to try to make this brief, and I'm not going to take the time to make like formal slides or something just because I don't think it's worth the time. I'd rather just get this done and get it out to you so that you can watch it whenever you feel like. So today we build on what we did last time by introducing these notions here: standard deviation, variance, and normal distributions. Extremely important for statistics. If you've ever seen a probability density function in your life and seen it applied, you've seen a normal distribution. As we will see in the next few sections, almost all of statistics runs off of these things. Like, you can't really overstate how important they are. So when I say the most important, I really mean that. I'm not saying one of the most, I'm saying the most. And we'll see why it's the most important distribution in section 5.4. Okay, so let's start with our first definition. So if x is a continuous random variable and it has some average mu, so we talked about expected value in the previous video, the expected value of a continuous random variable. The variance is defined like this. It's another integral, but now it's x minus the average value to the second times f of x. And the notation is sigma squared of x. So sigma squared of x is this integral. The standard deviation, denoted sigma of x without the squared, is simply the square root of this. So once you know the variance, you know the standard deviation pretty quickly, and vice versa. Now, before we move on, let me point out expected values are their own integrals. So I will show you the computations here in a second, but before you do this integral, you have to do this integral, the expected value integral. You get that value slotted in, and then get a new integral going if you're asked about variance or standard deviation. Now, what is the point of these definitions? Well, expected value, that's measuring kind of where the data is centered. We didn't really talk about that in the video, but sort of you're trying to find kind of like the tipping point for the data, like where's the middle of it? And if the data curve is symmetric, you're just literally pointing to the middle of the data. An expected value is like an average, and averages are trying to give you like a typical outcome, a middle outcome, however you want to say that. It's an average. Standard deviation and variance are not trying to measure the average. They're trying to measure the spread of the data. How spread out is the data? Is the data super clustered, or is there a ton of spread? The bigger the standard deviation, or the bigger the variance, the more spread there is. And to be a bit more precise, you're talking about spread about the mean or the expected value. So once you know the expected value, how spread out are you around that? I'm going to show some pictures here in a second to make this more concrete, but this is the punchline. The bigger the sigma value or the sigma squared value, well, I should be a little careful, but this is certainly true. The bigger the sigma value, the more spread there is in the data. As a useful aside here, one or two of the homework questions, I forget, asks about standard deviation or variance, but with a discrete random variable. So notice the setup here for a continuous one. Integral is like a big sum, so you're summing over everything. And then notice outcome minus average times probability is how you would read that in English. So look at this. Now we're just going to sum, but if x is discrete and finite, then you only have so many values. There's a finite number of values. And so here's outcome minus the average squared times probability. So these two formulas are completely in parallel. It's just the context changes If you go to a continuous random variable, you can't do a literal sum anymore because you're going over the entire real line. So you get integral, which is a limit of a sum. But again, like if I gave you this formula and said, what would that formula look like if x were continuous? You would kind of have to write this down. There's really no other option. So these are like two sides of the same coin, where when you flip the coin, the context changes. But anyway, okay. Next question is, why define both of these things? Like what? I have the squared and then the square root. Like, just pick one, you know? So why bother with two definitions? They both get their own name. What's the deal with that? Like, we don't have a name for pi squared. It's just called pi squared, right? Pi is the thing we care about. Anyway, so why have two names? Well, I mean, the answer should be unsurprising. They have different uses, actually. And each measure has advantages and disadvantages. So with variance in particular, the reason people care about that is more the theoretical people. A lot of theorems are much easier to prove if you're working with variance. And some formulas are much nicer to state if you're working with variance. This should not surprise you because standard deviation involves a square root. Boo, square roots. Square roots are not nice if you're trying to do algebraic manipulations or something. So anyway, the variance doesn't have a square root, so it's nicer. And here's an example. Let's let the covariance of two variables be denoted like this. Now, I don't assume you know what covariance is, and I'm not going to give you the real definition because I don't really care. I'm just trying to give you an example. Covariance is a measure of how closely connected these two variables are. Are they super closely correlated, or do they have nothing to do with each other? If the covariance is 0, that means they have nothing to do with each other. But the more closely positively correlated the relationship is, the bigger the covariance. So here's a nice little theorem that I'm not going to prove to you or justify in any way. But basically, variance is linear, kind of. So you can almost split variance over a sum, but you pick up this little, like an error term at the end. So the covariance is like measuring sort of the error. It's like an error term on the additivity of variance. And notice, by the way, if x and y have nothing to do with each other, so the covariance is 0, then the variance is literally linear. You can split it over the sum. So that's nice. Now, one reason you might not want to deal with variance is that it doesn't have the same units as x. It has units x squared. So let's say x is like measured in seconds. Then the variance has units second squared, which is maybe kind of obnoxious. I mean, I don't like to think about units, but that seems obnoxious to me. Or if x is measured in dollars, then sigma squared would be dollars squared. What does dollars squared even mean? Anyway, standard deviation, the big advantage of it is that it has the same units of x, so you don't have to do any like translation of units. So that's nice. Also, normal distributions, you can actually express them much more nicely in terms of the standard deviation than the variance. An obvious downside of standard deviation, it has a square root. So boo to that, especially when it becomes when it comes to dealing with formulas. That's a mess. Okay, so now let's do some examples and get out of here. So here's an example from the previous video. You should recognize this, a probability density function for waiting on hold. So there's no such thing as negative wait times. So this function really only comes online at x equals 0. So the question is, what are the variance and standard deviation? So we'll calculate the variance, and then standard deviation is just the square root of that. So here's the definition of variance. As I said before, first you need to know what the expected value is. So let me bring up here. Okay, this is an integral we looked at last time. So you take the probability density function, which is 3 over x plus 1 to the 4th, multiply it by x, and technically what you're doing is integrating from negative infinity to infinity. But as we talked about last time, this function here is 0 from negative infinity to 0. So you just forget about that piece of the integral and just deal with this function when it's live. And we get an expected wait time of a half. So that's from the last video. So now that we have that half, we slot that half right here. So x minus half. So now I come here and be like x minus half to the second, like that. So probability density function is the 3 over x minus expected value squared. And again, I'm still going to integrate from 0 to infinity because I still don't care about anything to the left of 0. And there you go. So there's the variance of wait times. And then if you want the standard deviation, all you do is take the square root of 0.75. So there you go. There's an example. So again, you have to be careful with a couple of things. First of all, if you're given a piecewise function like this, make sure you only do your integrals where the function is really live. If the function is 0, you don't care about that piece of the domain. So forget about x less than 0. Also, again, you have to do this integral up front to get the expected value. Okay, so what that means is, I mean, you have like no context yet. I'm not assuming you've seen statistics before, so I assume you have no context for this number. But the bigger this number, the more spread out the data is. So this number is fairly small. It's under 1. That means that this density function is not very spread out. It's pretty scrunched. And we actually looked at the graph last time. So recall the graph has data really clustered around 0. So this function, it starts super big around 0 and then dies out real fast. So that's what you're seeing with the standard deviation. There's not much spread. Okay. So here's another example. So, okay, trying to decide on an investment firm. Company A, Company B. So X represents the rate of return from Company A, and Y represents the rate of return from Company B. So, you know, if Company A gives you 20% return and Company B gives you 1% return, there's no question. You should go with Company A. Okay, so here you go. Here are probability density functions for how the firms perform. So Company A does this, Company B does this. So the first question is, on average, what return rate should you expect from each company? So on average, what do these companies do for you? So that's a question from last time. So I've got some integrals set up here. Okay, now I really do integrate from negative infinity to infinity because it's not piecewise or anything. So notice right here, this is the probability density function. I slot an x in there. That's from the definition of expected value. And this is for Company A with the 0.008. So there you go. On average, they're going to give you a 4% rate of return. So that used to be pretty good, but now inflation is higher than that. So now that's kind of sad. But anyway, that's what Company A will do for you on average. So again, there's no guarantee they're going to get this for you. Maybe they'll do way better, maybe way worse. But on average, that's what they'll do. So their average customer will see that. Okay, so the other one now, 0.02 is the only difference. Okay, so right here. Oh no. No, Wolfram. Don't freeze, Wolfram. Not in the middle of my video. Okay. 0.02. 02. Also 0.04. So what that means is that on average, these companies are the same. So if all you care about is average performance, there's no distinction between the two companies. Okay, so write that down right here. Now, the reason I give this example is to illustrate why you might care about standard deviation or variance in the first place. So we'll do that in a second, but now let's focus on this question. What's the probability? Oh, that's pretty good. So what's the probability maybe you'll beat inflation based on return rates? So 7 or higher. So if I come back up here, I have, this is Company B. So 7 or higher means I put a 0.07. And now, remember for part 1, expected value means I throw an x times these functions. So x times all of this, x times all of this. But this part 2 has nothing to do with expected value. It's just a straight up probability question. And when you do a question like that, you're not multiplying by x times. You're just literally integrating the probability density function on the appropriate interval. So I'm going to take that x times out of there. Okay, So this is company B. There's a 0.1% chance they get that nice performance for you. So it's very unlikely if you go with company B that you'll hit a home run. Now for company A, all you gotta do is switch these back like that. Okay, look at that. 6.6% or so. Now 6.7% is not a big probability, but like relatively it's way, way bigger than company B. So you're much, much more likely to hit a home run with company A than company B. So let's keep that in mind for a second. If you're swinging for the fences, company A is more likely to do that for you than company B. Now let's see what variance and standard deviation have to do with any of this. Okay, so for both companies, 0.04 was their expected value. So I'm going to come back up here and x minus 0.04 to the second like that times, and I got to go from negative infinity to infinity like that. Let me make sure I did this right. So this is for company A. Here's their variance. So again, if you want standard deviation, just take the square root of that. So their variance is 0.0004. Now I'm going to copy and paste all this and open a new window so I have it. Here's company B. Company B's average value is the same as company A's, so I can keep that 0.04. Okay, 0.001. So again, let's just compare these. 0.0004 to 0.0001. So notice the variance of company A is much higher than the variance for company B. So what that means is, I mean, they're both small, aren't they? But this is 4 times bigger. What that means is that this data here, company A's data, is like, I'm not sure how rigorous this is, but 4 times more spread out than this data. It's much more spread out. And to see that, let me show you some pictures. This is company A's probability density function. So notice there's actually quite a bit of area over here where the rate of return is negative. So this right here, this is like 0.04. That's where the data is centered. So if your distribution is symmetric, and this is, the expected value is right in the middle. So this is 0.04 right here. So the probability you get a negative rate of return is non-trivial. Look how much area is there. But like right here is 7%, something over here, like this is 7% rate of return, because there's a 0.07 down here. Look at all this area over here. So there's quite a bit of area over here in like the home run section or something, right? Where you get a really good big rate of return. Now the other company, this is their probability density function. See that? So their probability density function is much more scrunched. So you can see the less amount of spread. You can also see why it's so hard to do super well with this firm. Right here's like 7% right here. See how there's like no area right here? Yeah, so it's hard to do super well with company B. However, notice the probability of getting a negative rate of return is essentially 0. So this curve dies down before you go negative. So that's the difference between the two firms. On average, they do the same for you, but one of the firms has much more spread out data than the other. And that comes with a trade-off. So if you have a higher risk tolerance, you go with this lower curve, because there's a higher probability you get over here. And then you have to tolerate that sometimes you might go negative. If you want like slow and steady, like you want something predictable, you go with company B. Company B is much more likely to just get this 4% or something close to 4% for you. So if you're a more conservative investor and you just want to like make sure you don't go negative and you want sort of like reliable rates of return that don't wiggle around too much, you go with company B. Okay, so hopefully that has fleshed out what these things are telling you and why you would care about them. And again, if you want standard deviation, just take the square root of the numbers we got, and everything I just said still applies. Standard deviation is also, it's just a measure of spread. It's also measuring how scrunched or how spread out your curve is. Okay, finally, we end with this, normal distributions. Again, all of you have seen these before, I'm sure. Normal distributions are called bell curves because they're shaped like a bell. They look like this. So this, what I have on the screen here, these are both normal distributions. They're bell curves. So every normal distribution is completely characterized by its average value or expected value and its spread number, sigma, where now we're talking about the standard deviation. So what I mean by that is if I tell you, hey, this normal distribution has an average of 10 and a standard deviation of 1, there's one and only one curve that looks exactly like that. So those two parameters tell you precisely which curve you're talking about. If I tell you, hey, its expected value is 10, and then I say nothing else, there are lots and lots and lots of normal distributions that are centered at 10. So you can't know exactly what curve I'm talking about if that's all I say. So anyway, here's a schematic of normal distributions. And the way this is expressed, it shows you what happens to the curve as you move away from the center. So if you take one standard deviation step away from the expected value, see how there's still a ton of area here? So getting a value that's one standard deviation away from the center is not particularly surprising. But notice by the time you get to 3 standard deviation steps away, there's like barely any area left. So of all that to say, that's encapsulated in this rule here. 68% of the data for a normal distribution lives within 1 standard deviation step of the expected value. So in terms of integrals here, if I draw a dotted line right here, and then another dotted line right there, that's what I mean by within 1 standard deviation step of the average or the expected value. 68% of the data lives there. So the probability a randomly selected individual or whatever, the probability to live in this range here is 68%. And then here a similar number is 4, 2 standard deviation steps, and 3 standard deviation steps. So see this 99.7? So 99.7% of your data will live within 3 standard deviation steps. So the probability you see something outside that domain is very small. So let me finish with this example here. Blood pressure in adults is normally distributed approximately, and the expected value is 85, so that's mu. So sometimes I just say mean instead of expected value, but it's the same thing. So mean of 85, and then sigma is 20. So I could ask you, what's the probability a randomly chosen person has blood pressure 135 or higher? And then you could go to the calculator, you could plug sigma and mu into this function and just do like this. So set up, and maybe since we're here, let's do that. I know I say here, hey, don't do that, but let me just show you since we're here. Okay. Actually, do I feel like doing that? I guess I don't. I'm backing off. Anyway, but without doing that integral, we should anticipate a very small probability because 85 plus 20 is 105. And then 105 plus 20 is 125. And so this 135, it's more than 2 standard deviations away from the average, more than that. So if you want to move that far away, you've already missed 95% of the data. So there you go. So by the time you reach 135, in terms of a picture like this, you're like right here. So there's just not that much area left. So it's not like infinitesimal, but you're starting to get in this tail right here where there's not much data left. Okay, now the last thing I want to say is, wow, wasn't it obnoxious writing all this out, this stuff? It was so obnoxious I did it before the video started. As you might expect, normal distributions are so important and so prevalent that there are just online calculators where you just tell it, like, hey, my average value is 0.04, my standard deviation is 0.008 or whatever, and you give it a range. You say, I want the entire data set maybe, or I want from 2 to 5, whatever. You just tell it those things. It then builds and calculates this integral for you. So I'm going to show you that, I guess, next week. But if you're alarmed by all this nonsense here, like, do I really have to type that every time? No, not every time. Not for normal things. So I'll show you that next week. But yeah, it's sort of tiresome, and it's very easy to mess up your parentheses. That's why I did this ahead of time, so you didn't have to watch me mess up my parentheses. Typing things like this is not something decent people really do in public, so I did it in private before hitting play. So anyway, so don't worry about that. I'll give you a calculator next week that just cranks these probabilities out, or these numbers out right here. I guess this wasn't a probability. This is a variance. But, again, suppose you're not doing a variance. Suppose you're doing a probability from okay. So this is the probability you get a positive rate of return from the company. So there's like a 97% chance of that. So again, there's an online calculator where you tell it 0.04, 0.008, 0, infinity, and it does this for you. It just cranks out that 97.7%. Okay, so hopefully this was all right. Again, if you want to meet with me sometime, you can meet with me during our class time tomorrow after convocation. As always, though, as the syllabus says, you can schedule a time to meet with me anytime. So if you want to meet next week and talk about this, you can. Yeah, so we're done for now.